Greetings, AP Stat students. Today we are going to begin Chapter 5, which is probability. What are the chances? We're going to be really centered on probability in this chapter, and we're going to be discussing the rules for probability and just some various things that have to do with probability. Today we're really going to be kind of looking at randomness, just the idea of probability, and simulation, how we can simulate things that happen by perchance. How can we do that in various different ways? So hopefully find this chapter will be a little bit more like the math that you've seen before. You've done some of the probability stuff before. But this first section may not be quite like that. But once we get past this first section, it really should start to, at least we're going to be calculating something again. Chapter 4 is it's probably the weirdest chapter to teach in a math classroom because it really does kind of feel like anything but math, really. So we're past that now. We're past that. You don't have a test. You don't have an additional test over it. I took that quiz, the 4.1 and 4.2 quiz, and changed that to a test. So I am looking at the possibility of combining 5 and 6 into a test. Even though it is two longer chapters, I think that they can go well enough together to make it into something where we could actually do this. We could actually go through and be okay with that. So I'm looking at the possibility of combining those into one test and having another 100-point test again, because we haven't had a 100-point test since the 2 and 3 test. So we'll look at that. We'll discuss that. I'll think about that. All this just kind of depends on a lot of things. But today we're just going to start with section 5.1. Again, I'll have the notes for you on the first day that we're back together in person. I'll have these PowerPoints for you. Okay, but I will post a handout of them on Google Classroom, of course. So we're looking at randomness, probability, and simulation today. All right. So randomness, probability, and simulation are objectives. There's only really two objectives for this. We're going to interpret probability as a long-run relative frequency, and we're going to use simulation to model chance behavior. So the first, the idea of probability. Chance behavior is unpredictable in the short run, but has a regular predictable pattern in the long run. This brings in something called the law of large numbers. Okay, the law of large numbers. Let me move this out of the way here. All right, so the law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. Okay. So, for instance, this is looking at tossing a coin and the proportion of heads. So we toss the coin once, and on the first time we get a heads. The next time we get a tails. So 50% at that point, we'd had one heads, one tails. And we have another heads, so it's 70. It's going up to 75% heads there, roughly somewhere around there. Then it's back to we get another tails. Then we got another tails, so on and so forth. And after you do this so many times, if we simulated that, after right here, this just goes up to 20 times, but here's up to 500 times. You can see that the proportion of heads is approaching that middle line, which is at 0.5, so 50%. So if we do that enough times in, a bunch of times, many, many, many trials, we should have 50% heads. And then obviously that would be 50% tails as well. That's what the law of large numbers is. We observe these chance processes, whatever it may be. Here's a flipping a coin. Over time, those proportionate times a specific outcome occurs will approach a single value. Doesn't always have to be 50%, though, by the way. If you have more possible outcomes, that's because it's 50% in this case because you're flipping a coin. You're going to get one outcome or the other. but it could be you're drawing a card from a deck of cards, where you replace it on the bottom of the deck or whatever, and you shuffle after so many times or whatever. I don't know. Or shuffle after each time, and it's random. So it could be that you have more possible outcomes, though that means the value will approach something else besides 50%. The probability of any outcome of a chance process is a number between 0 and 1, and that describes the proportion of times the outcome would occur in a very long series of repetitions. Okay, it is important to note that probability is between 0 and 1. Okay, any probability will have to be between 0 and 1. All right, so the idea of probability seems straightforward. However, there are several myths of chance behavior that we must address. First, the myth of short-run regularity. The idea of probability is that randomness is predictable in the long run. Our intuition tries to tell us random phenomena should also be predictable in the short run. However, probability does not allow us to make short-run predictions. Okay, does not allow us to do that. So, your book has some, as always, your book goes through and explains that about the coins, throwing, flipping a coin and how that, goes through and kind of talks about that. But we could also look for a slightly different, there's some other explanations that your book goes through. I really encourage you to look at your book and maybe actually read through some of the examples that go along with this. You could even stop the video here and go do that for short run regularity. That starts on page 287 in your textbook at the bottom there. There's an example about coin tossing. There's also another example about a shooter having a hot hand in basketball. Okay, which that may or may, for some of you basketball players, since there's several of you in one of my classes at least, that may you may have your own thoughts about that one. But anyways, then you got the myth of the myth of the law of averages. Probability tells us random behavior evens out in the long run. Future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of an individual outcome occurring in the future. Each outcome is going to be have that chance. The past outcomes are not going to influence that likelihood or that probability of that outcome occurring in the future. All right, so simulation. The imitation of a chance behavior based on a model that accurately reflects the situation is called a simulation. To perform a simulation, first you want to ask the question of interest about some chance process. You want to look and see what it is that they're asking, or what is it you're wanting to ask about the chance process. You want to describe how you're going to use a chance device to imitate one repetition of the process. The chance device may be flipping a coin. It may be drawing a card. It may be using the random number generator on the calculator. And I realize I've not showed you all how to do that effectively. I can't remember actually. If I did, I don't think so. I don't think I've showed you all how to do that yet. I meant to do that in the with the last chapter actually, but I don't think we actually got around to actually showing you how to do that. So I'll have to do that at some point. So, but it may be using whatever kind of device, deck of cards, coin, calculator, computer, whatever, to simulate this. What device are you going to use to imitate one repetition of the process, and then tell what you will record at the end of each repetition. So, we're imitating a chance behavior. Let's say that a baseball player has, for whatever reason, how we know this, I don't know, but let's say that he has a baseball player. He has a 65% chance of hitting the ball. So if you want to do a simulation of this with a random number generator, you could use the numbers between 1 and 100 and you could use the numbers 1 to 65 to mean that he hits the ball, and from 66 to 100 he misses. And then you could just do a random number generator. It'll generate a random number between 1 to 100, and you can see whether he hit it on that particular try or not. You could also do that with the table of random digits too, by the way. We did talk about that in the last chapter. The way you would want to do that is you could use 2-digit numbers, and you could use 00 to 99. And you could say that 00 up to 64, that would be 65. Or you could do this. It would be easier probably to do this. Do 01 to 65. 01 to 65, 2-digit numbers, means that he hit the ball, but 66 to 99 and also 00 means he misses. And then you could just use a random line in a table of random digits that way. But you're going to have to describe how you do that. You're going to have questions today where you're going to be given a chance process like that. You're going to have to logically think, how can I use this device? Or maybe you get to pick a device, but there's some where they're going to say, hey, here's your device. This is what you got. How are you going to simulate this situation using this device? So it's going to be a little bit of thinking outside of the box today. Okay, like I said, this section is a little more thinking, not a whole lot of calculating. But we will get into calculating probabilities with the next section. And then you actually do perform the repetitions of the simulation. You can actually, with a random number generator on the calculator, you can have it generate multiple numbers at the same time. You can tell it how many you want to generate as well. So that's really neat if you to do that as well. And then you conclude, based on the results of the simulation, you answer that question of interest. So we can use physical devices, actually random numbers like table D. It could be used technology. Like I said, coin flipping, cards, whatever. All right. So here's an example of simulations with technology. We're actually going to talk a little bit about the random number generator right here. And I may be able to have your calculator with you because I may actually walk you through how to use that, how to do that real quick on the calculator. All right. So in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of these NASCAR drivers. Again, this is a little bit dated. Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, and Jimmy Johnson. So the company says that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 driver's cards. She is surprised when it takes her 23 boxes to get the full set of cards. Should she be surprised? Well, problem. What is the probability that it will take 23 or more boxes to get a full set of 5 NASCAR collectible cards? That's the problem. So plan. Well, we need to number the 5 numbers to represent the 5 possible cards. So we'll say 1 is Jeff Gordon, 2 is Dale Earnhardt Jr., so on and so forth. And we'll use a random number generator right here. The way you get that notation right there, rand int, on the calculator, guys. Here's where you want to have the calculator in front of you, please. Go to math. Go over to PRB. I forgot to mention that this is another place on the calculator we will go to sometimes in stats. Math, PRB. You went to this in Algebra 2, though. You used NPR and NCR for permutations and combinations. And also number 4 is factorial. So all of those come from Algebra 2. But rand int, random integer is what that stands for, by the way. Rand int, that's random integer, is option number 5. And if you tell it 1 to 5, what that's doing is you're doing from 1 to 5. I'm going to pick a random integer starting with 1 up to 5, somewhere in between there. And including 1 and 5, of course, in this instance. Okay. Now, you could also put, after the 5, you could put a comma. Don't do this because we're not wanting to do it because that's not the way they're telling us to do it here in the problem. But we could put a comma after 5, and then we could put in another number, and that number would tell the calculator how many random integers from 1 to 5 do you want? And it'll actually spit out an entire group of numbers for you. But if you just do 1 to 5 like this, it's going to give you one number. So like I hit enter and I got 4. You hit enter, you're going to get a different number because it's random. Okay, you're probably going to get a different number. Some of you will get 4, but some of you will get 3. Some of you will get 2. Some will get 1. Some will get 5. Okay. Now, because we want a full set of cards, we'll keep pressing enter. So you'll hit enter again. It just does it again. So I hit enter again. I got 2 the next time. You're going to keep going until you get all 5 numbers. Okay. So I got 4 and 2 so far. Why don't you stop and actually do this now? Okay. Hopefully you got your calculator in front of you. You actually go through and see how many times it takes you to get all of them. Oh, I got 1. Yay. 3 boxes in. I've got 3 different cards. Up, I got 4 again. Okay. Write this down like, you would want to record this probably in a table, and you would want to say you'd probably want to number your tries on one side and your results on the other. But it looks, after 4 tries, I've gotten 1, 2, and 4 so far. But I'm missing 3 and 5. I'm going to keep going. Try number 5, I get a 1. Darn. Try number 6, I get a 4. Darn. Try number 7, I get a 3. Okay. Try number 8, I get a 5. It took me 8 tries. Yay. I got it in 8 tries. I only had to buy 8 boxes. You keep doing it and see how many times. Pause the video right here if you need to. You keep doing it and see how many times it takes you to get all 5. All right, so here's the results here. One person, it took them 9 times. Another one, it took 16. Another one took 10, 15, 22, so on and so forth. So, conclusion. We never had to buy more than 22 boxes to get a full set of NASCAR driver's cards and 50 repetitions of our simulation. So, our estimate of the probability that it takes 23 or more boxes to get a full set is roughly 0. The NASCAR fan should be surprised by how many boxes she had to buy. She just had a bad case of luck right there. All right. Hopefully that's been helpful. Like I said, you're going to take some of the problems you're going to look at today. You're actually going to go through and talk about how you would use a simulation to do that. And another device I didn't mention was a dice. Obviously, you could use a 6-sided dice. You could use a dice that has more sides than that if you wanted to. So your answers to some of these questions are going to be a little bit more inventive. And so if I were to do I'm not saying right now I'm definitely going to, but I'm leaning towards doing a free response question or possibly free response questions for this next test. This is probably one of the sections that it would come from, because this is more of a thinking type section. It's more of a, let's discuss it, let's talk about it. Or it could very easily be that you actually have to talk about simulation as one part of a question even. Maybe I have you calculate probability on the other parts or something. So just so it's not all about the simulation. But anyways, you're going to practice with this a little bit. So you have to kind of think outside of the box a little bit on how you're going to use that. And if you come up with an answer, it may be slightly different than the answer in the back of the book, but it's still correct. So you have to be a little lenient on yourself as you're going through and looking at the answers there. All right. Hopefully, like I said, this has been helpful. Let me know if you have any questions.